So again, yay, glad to see everybody here. You're gonna let me know how that focus is, and it's day 13. Welcome. So of course, the big announcement is that test 3 is in 1 week. And that, of course, is going to be July 18th. And this is the deal. We're going to have the exam from 7 to approximately 8:30. And that means at 6 p.m., we're going to have just a Q&A until 6:45 p.m. So last minute questions we can do. Then we'll take a little break and regroup and start the test at 7. Any questions? Maybe you want to know what sections we're going to be covering. Well, it's you need 5.1, even though we've been tested on 5.1, we still need that stuff. So it's 5.1, 5.2, 5.3, 5.6, just a little bit in 5.6 tonight. Then 7.1, 7.2, and 7.3. We're going to cover that tonight. And chapter 8, 8.1, 8.2, 8.3. And I've already dropped the first video for section 8.1. So see the new playlist in YouTube, and I will be getting those notes up right after class. I just got that recorded this afternoon. Over the course of the next 12 hours, I'll be dropping videos on all this material so that you can go ahead and work through that, at least watch those videos before class on Tuesday. That way, hopefully in class on Tuesday, it'll be more of a workshop than a lecture, okay? Because you only have 2 days then, and you'll be tested on that. So that's why I'm dropping the videos tonight and tomorrow on chapter 8 material. You are welcome. So our goals today are, we're just going to say a little bit about section 5.6. We already talked about the bunny rabbits. That was our first recursively defined sequence. So we're going to look at a few more examples of recursively defined sequences, and then we're going to call that enough. Then we're going to start chapter 7 tonight and finish it. We're going to look in 7.1, definition of a function. We're going to also look at numerous examples. And then we're going to look at non-examples, relations that aren't functions. We'll look at some arrow diagrams because that is a nice way to see a picture of a function. We're going to talk about images and inverse images of functions. I'm not talking about an inverse function, but inverse images of sets and elements in the codomain. Then we'll talk about the 2 big properties of a function and properties of functions. This is the shorthand for functions, FXS. There are 2 big properties, the one-to-one property and the onto property. Then in 7.3, we're going to talk about function composition. We'll be attacking that with some diagrams as well as with some algebra. And then we'll be asking and answering this kind of big question: when does a function have a functional inverse? A true inverse, in the sense that the inverse is itself a function. So that's the lay of the land tonight, folks. Let's get started. So example 1. So say we have a sequence. We're going to talk about recursively defined sequences. This is section 5.6. Say we have a sequence defined by, here we go. A naught is 2. A sub 1 or A1 is 3. And A sub k is defined to be A sub k minus 1 plus A sub k minus 2 for k greater than or equal to 2. So this is the recurrence relation, and it should look familiar because it's the same recurrence relation that appeared in our Fibonacci sequence that we saw at the end of our last lecture. And these are the initial terms. Okay, so what we'd like to do is find A2, A3, and A4. All right, so because we have a naught and we have a 1, so the next term, of course, that we want to find is A2. So 2, that indexing number, is in the range k greater than or equal to 2. So it is a k that is large enough for us to apply the recurrence relation. So we use that. So the recurrence relations for k equals 2, maybe I want to put that here. For k equals 2, we're looking for A2, and according to this definition, it's A sub 2 minus 1, k minus 1, plus A sub 2 minus 2. So we do a little bit of arithmetic here in these indexing numbers, and this is pretty easy. I mean, you should be able to kind of naturally understand that k minus 1 is the integer right before k, and k minus 2 is the integer right before k minus 1. If you drew a number line, you would see those, like here's k, the one right before it is k minus 1, the one before that would be k minus 2. Of course, the one after it is k plus 1, and so on and so forth, right? So we're looking at A sub 2 minus 1. That is A sub 1 plus, because that's what this recurrence relation says. It says we're going to add together these two prior terms. And of course, 2 minus 2 is 0. So we're looking at A1 plus A naught. What is that, folks? Anybody?
5.
Sure. How'd you get 5?
3 plus 2.
Sure, because A1 is 3 plus A naught is 2. So this is 5. Yay. Can everybody find A3 and A4 now? See if you can find A3 and A4. Everybody getting A3 equals 8 and A4 equals 13? So yeah, good. And these look familiar, right? Because when we played the game with the Fibonacci sequence, since it had that same recurrence relation and happened to hit the value 3, then the rest of the sequence looks like the Fibonacci sequence. It's not the Fibonacci sequence, but it's very similar, just different initial terms. Okay. Any questions? So let's do a different example where the indexing variable k appears not just in the indexing expression, but also in the general recurrence relation expression. So example 2. Find the first 5 terms of the sequence defined by. So I'm just trying to give you kind of a little different instruction here. B1 is equal to -2. B2 is equal to 4. And B sub k is equal to k times B sub k minus 1 minus 3 times B sub k minus 2 for k greater than or equal to 3. So again, we have our initial terms and we've got our recurrence relation, but the indexing is a little bit different here, right? Because this sequence starts with B1 instead of B0. Notice in our recurrence relation, the k appears as part of the formula, not just in the indexing numbers. Now, it says find the first 5 terms. Well, B1 is the first term and B2 is the second term. So we do include those because we were asked to find the first 5 terms. So the first term is B1, it's -2, of course, and B2 is 4. Now, for k equals 3, 3 is big enough for us to start using the recurrence relation. So B sub 3 is now, according to this formula, k becomes the coefficient of the B sub k minus 1 term. Well, k is 3, so it's 3 times B sub 3 minus 1 minus 3 times B sub 3 minus 2. Everybody with me? So it's 3B sub 2 minus 3 times B sub 1. And now we grab the B sub 2 and B sub 1 values that we have up here. So it's 3 times 4 minus 3 times -2. What does that become, folks?
$18.
Sure does. 18, 12 plus 6. K equals 4. 2 more to go. B4 is 3. Nope, 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 nope. It is not. It is not 3. What's the coefficient here going to be?
Four.
Yeah, it's 4. B sub k minus 1 minus 3B sub k minus 2. So it's 4B3 minus 3B2, of course. So it's 4 times 18 minus 3 times 4. So 4 times 18 is 40, 72 minus 12. I'm getting 60. Anybody else getting 60? I hope you are. Okay. K equals 5, and we're done here. Just a little practice with recursively defined sequences. Everybody see if you can find B sub 5. I meant to put a 4 here for the K and a 4 here for the K and B4. 5 minus 1 minus 3 B sub 5. 5, 4 minus 3 B3. So it's 5 times 60 minus 3 times 18. 300 minus 54. I think that's 246. Anybody else getting 246? How you doing, Favor? Good to see you, man. So there are, I don't know, 4 problems from section 5, 6, in WebAssign, they've been up since yesterday, so go ahead and work those. Folks, you cannot get behind in WebAssign now. You have got to keep up. Now, you know, if you need, you know, 1 extra day or something, go ahead and ask for that, you know, so that I can give that to you. But you don't want to start falling behind now because we are at the 11th hour. That's all we're going to do with recursively defined sequences. I just wanted you to see these because they crop up in programming a lot. Questions? All right, of course, we already worked through chapter 6 concepts. We are now in chapter 7. Just recall the cross product of 2 sets, A cross B. The elements, it's a set, of course, so we open set brackets. The elements are ordered pairs. So of the form, say, little a comma little b, it's parentheses, of course, these are ordered pairs, such that little a comes from the set big A, right? And little b comes from the set big B. So of course, just to remind, this is called an ordered pair. I think everybody knows that here. And we have 2 coordinates, right? A is the first coordinate, and B is the second coordinate. Right, we have 2 coordinates, A and B, first and second coordinates. So here's an example of a familiar function. But it may not be the way that you are used to writing it. But this function, I guarantee you, you know this function. I'm going to start with example 1 again now that we're in a new chapter. F is going to equal the set of ordered pairs of the form x comma x squared, such that x is in the reals. Now we are told x is real. So we know this first coordinate is a real number. The second coordinate is x squared. Well, that's going to be real, of course, if x is real. And so this is a function from the reals to the reals. This f is actually a subset of the reals crossed with the reals. Both coordinates come from the reals. You probably are familiar with this other notation. F of x equals x squared. Or you probably saw in high school, y equals x squared. You know, this is your basic parabolic function that's got the vertex at the origin, right? If we graphed it, it looks, you know, like that. Something like that. Not quite like that, but right. Okay. So, but this is the notation that is more common at this level, is for this course, because it's a discrete math course. So we like to think about the points on this curve as ordered pairs. You know, like the point 2, comma 4. And we think of the first coordinate as the x coordinate and the second coordinate as the y coordinate, right? Look, y is f of x. Now this is f of x. X squared is y. That is the function value at x. X is the independent variable. Y depends on x. So, depending upon what x is, y will take on particular values, the square of x. So let's get a formal definition now of a function for our purposes. A definition. Here we go. Given non-empty sets A and B, a subset of A cross B, we'll call it F for function, obviously, is a function from A to B That's what we're defining, a function from A to B. And it's denoted by this notation. This notation is reserved for functions F colon A arrow to B. And that's the way we read it. We read this F from A to B. So a subset of A cross B is a function from A to B if two things happen. One, each X in set A has at least one corresponding value Y in B such that the ordered pair X comma Y is an element of F. And two, each X in A has at most one corresponding value Y in B. Such that the ordered pair X comma Y is in F. So we have at least one corresponding value Y and at most one corresponding value Y. In other words, each X in A has exactly one corresponding value Y from B such that XY is in F. The existence of at least one Y for X is called like the existence clause. There does exist a Y that pairs up with X. The at most one corresponding value Y for X is the uniqueness clause. The corresponding Y is unique for X. Okay? So we say the image of X exists. And here we say the image of X is unique. So it's an existence and uniqueness claim about a partner Y for the X coordinate. Now notice set A, this is a function from A to B, is called the domain of F. So we're going to get a little bit more bang for our definition buck here. A is called the domain of F. And set B is called the codomain, not the range, folks. The range is something else. B is the codomain of F. So the domain, the codomain. If X comma Y is in F, we also write F of X is equal to Y. And that's probably the notation that you're used to seeing. Okay. All right, let's look at some examples. More. Example 2. Let's let A be the set containing little a, little b, little c, little d, little e, and B be the set containing little s, little t with a tail, w, y, z. So just a couple of finite sets. We're going to look at a finite function here. So 1, consider this subset of A cross B. I'm going to call it F. F is a set. It has ordered pairs because it's a subset of A cross B. The first ordered pair is little a comma t. Second ordered pair, B, T. Third ordered pair, C, Y. D, Z. And E, comma T. Close that up. Is F a function from A to B? And we're going to explain or verify. So what are we checking? We're checking that each X in A, because the first coordinates are coming from set A, has at least one corresponding Y value from B, and that each X in A has at most one corresponding Y value from B. So let's check. Let's check these elements of A. They're appearing as the first coordinates. Let's make sure each one of those is paired up with exactly one element from B. Well, A has one image, namely little t. B has one partner, little t. C has one function value, y. I'm saying it a bunch of different ways. Z is paired up with, D is paired up with Z, and the image of E is T. So each of these second coordinates does come from B. No first coordinate is paired up with two different separate coordinates, second coordinates. So the answer is yeah. Yes. Each element from the domain A has exactly one, I'll put it in quotes, partner, what's also called an image from set B. Partner. Okay, so this is a function. Let's look at it. Let's look at another subset. Is G given below a function from A to B? Here's G, folks. It's the set that has little a, comma, little s, little a, comma, little t, little b, comma, little t, little c, comma, y, d, z, e, t. Is that a function from A to B? What do you think?
Yeah.
Speak up.
No,
No, why not?
there are A is matched with three things from set B, and T is matched with three things from set A.
So A is matched
So,
with two elements from set B, right?
yes.
It's not a problem that T is matched with numerous elements from A. Look, that happened in F. T was the image of A, T was the image of B, and T was the image of E. That's not a problem to have a second coordinate be the same for numerous different first coordinates. That's not what this definition says. This definition says that each X has exactly one partner. It doesn't say each Y can only have one partner. But it is not a function for what you said first, Hans, and that is A is paired up with S, but A is also paired up with T. And that breaks the uniqueness clause in the definition of a function. Each X and A has at most one partner. Sophie, question?
Yeah, I mean, you kind of just said it. I was just going to ask you if you can break down the definition again, because it seems like it's the same thing written twice, except for at least and at most. So it says X is an element of A, has at least one corresponding value Y in set B, such that X, Y is an element of the function. So it's the definition is just confusing me. So I don't really follow like the second. I mean, I don't really follow the examples.
Well, the definition says if you look at each element of A, these are the domain elements. Each one of these has to pair up with a Y. There's got to be a Y that it pairs up with. That's what at least one means. It means, there's got to be some Y that each of these will pair up. A's got to pair up with some Y, B's got to pair up with something from B, C's got to pair up with something from B. It doesn't have to be this Y, okay? Just, some element from B, okay?
Okay.
But at most one means if you look at an element of A, like this one, little a, it can't have two different partners from B. It's got to have one, but it cannot have more than one. Does that make sense? Well, see, that's what I'm trying to show you here.
Okay,
This is not a function because this A has two different images, two different partners, and that's not what a function can do. So the answer is no, because the element little a in A has images S and T from B, i.e. AS is in a G and AT is in G, violating part 2 of the definition of a function. Because part 2 says the image, the Y has to be unique, that each element in the domain has to have just one partner, and A's paired up with two different elements. Let's try another example. and see if we can understand it by looking at even more examples, okay? Is H a function from A to B? Here, I'll write the A up here where you can see it. A is a set containing little a, little e, and B is the set containing little s, little t, little w, y, z. And here's H. H has A comma S, B comma T, C comma W, D comma Y. And here's the definition of function, again, the two-part definition. Does H satisfy the definition of function?
Is it no?
It is no. Why do you think no?
Because it breaks the first rule.
Yeah, each element of the domain, each one of these elements has to have a image, a partner, a second coordinate that exists. You know, there has to exist a Y to pair up with A, and there has to exist some element from B that pairs up with little b, and there has to exist an element over here in the codomain that pairs up with C and with D and with E. But look, E doesn't appear as the first coordinate of any ordered pair. E did not have a partner. So the existence requirement of an image for each domain element fails for H.
Does it also fail for the second one as well, since it doesn't have any, the set doesn't have Z in it?
A, B, C, D. No, oh, no, there's no requirement that every element in the codomain is the image. It just requires that every element in the domain has an image.
Okay, thank you.
Uh-huh, good. So no, because E is in A, but E does not appear as the first coordinate in any ordered pair or of any ordered pair in H. In other words, E has no image point under H. It doesn't map anywhere. And I think the arrow diagrams that we're going to look at next are going to help with this concept. Let's look at some pictures. Arrow diagrams. For functions. You'll like these because pictures really do help. Here's our example 3. We're going to let set X equal the set containing 1, 2, 3, 4, and 5. And we're going to let set Y, big Y, be the set containing little a, little b, little c, little d, and little e. Oh, and little f. I want 6 elements. 1. Let H be a subset of X cross Y be the function. And I'm just going to go ahead and use functional notation, h from x to y, defined as follows. Here's h. H is the set having 1 comma little b, 2 comma little c, 3 comma little e, 4 comma little e, and 5 comma little c. Draw the arrow diagram for H. I'm going to show you how to do it, of course. And then the second thing we're going to do is we're going to find the range of H. We'll get a definition and we'll come back and we'll find the range of H. But first I want to draw the arrow diagram because then it's easier to talk about the range. All right, so to draw an arrow diagram, I'm going to draw kind of an oval shaped circle for X and an oval shaped circle for Y. These are my sets. And we're drawing H. I'm going to put the elements of X into this set X, and I'm going to separate them out so I can see, and I'm going to label on the left because I don't want my labels for my elements to get in the way of my arrows. So 1, 2, 3, 4, 5, those are the elements of the domain X. Now the codomain Y has A, B, C, D, E, and F in it, and I'm going to put its labels on the right of the points so that I'm out of my own way when I draw the arrows. Okay? All right, so how do we draw the arrows? It's exactly what you think it should be. 1 maps to B, right? This first order pair says 1 pairs up with B. 1 maps to B. So we draw an arrow from 1 to B. Folks, it's an arrow diagram. Line segments don't cut it. You have to have a tip pointing to the image. So the arrow goes from the domain, it initiates in the domain, it terminates in the codomain, so the tip is in the codomain. 2 maps to C, so I'm going to put 2 to C. 3 maps to E, okay, so 3 is going to E. 4 maps to E, okay, so 4 is also going to map to E. 5 maps to C. Okay, that's the arrow diagram. So notice this. The visual check that H is a function is this. Each element in the domain X has exactly 1 arrow coming from it and pointing into the codomain Y. Each domain element in set X has exactly 1 arrow coming from it and pointing to an element in the codomain Y. So if we went back, for example, and drew the arrow diagrams for function H, it's right up here. there would be no arrow coming out of point E. And that would be the visual check. You'd have a domain point that didn't have an arrow, and didn't have an image. So an arrow diagram makes it's easy to visually check. And the thing that went bad with the subset of A cross B, G that wasn't a function was that A would have two arrows coming from it. But what you want is exactly one arrow coming from it. See, that's what the at least one Y and at most one Y means. It means there's exactly one Y that pairs up with X. That's the significance of the at least one together with at most one. Questions? Let's define the range of the function.
I had a quick question about that. So on the test, when we answer, do we have, can we say, oh, this is not a subset by the second rule, or do we have to state what the rule is?
Ah, if I want you to know the number of the rule, I'll give it to you.
Okay, thank you.
Uh-huh. But you have it in your notes and you do get an open book test, right?
Right.
Given a function f from x to y, the range of f, that's what we're defining, the range of f, denoted by RNG of f, is this set. The range of f is the set of y in the codomain, big Y, such that there exists an element little x in the domain big X, where f of x is equal to y. In other words, folks, the range of f is the set of elements in the codomain that actually get hit by an arrow. That's the intuition behind this. The range of f is the elements in the codomain, here it's y, that get hit by an arrow. These are the images of some domain element, or several elements sometimes. So now if we go back and look for the range of H here, it's pretty easy to see the range of H. What is the range of H here? What are the elements that actually get hit by an arrow? Anybody?
B, C, and E.
Exactly. Now, if you don't draw an arrow diagram and you want to know the range of H, just look at the second coordinates. Those are the elements that would get hit by arrows, B, C, and E. It's okay that C gets hit twice. It's okay that E gets hit twice. Nobody says that's no good. Okay. And that brings us to the idea of the image and pre-image, but let's do one more example. Shall you, just one more arrow diagram here. So that you feel comfortable with this. Let's let X be the set containing 1, 2, 3, 4, and 5. And again, Y is going to be the set containing little a, little b, little c, little d, little e, and little f. And we're going to define K from X to Y. Folks, when I use this notation, K colon X arrow to Y, that means it is a function. We reserve that notation specifically for functions. So we're going to define K as follows. K is this set of ordered pairs. 1, comma, little a, 2, comma, little a, 3, comma, little a, 4, comma, e, and 5, comma, d. Draw the arrow diagram. Find the range of K. So we just, we want to get comfortable with doing this. Just want to make it large enough that I can really see, and make sure that you don't use line segments. These have to be arrows. So that's called an arrow diagram. This is for K. 1 goes to A, 2 goes to A, 3 goes to A, 4 goes to C, and 5 goes to D. What's the range of K, everybody?
A, C, and D.
Good. Thank you. Questions? Okay, so we've been going at it for an hour. I'm going to pause and you're going to. So we are back, and thanks for the 5-minute little breather here. Images and inverse images, because I've been using the word image, but we need a definition here. Let's get a formal definition. And then inverse images is when we look backwards and see what hits something. Images of a point, or what it hits. Maybe you'll take a few of the points in the domain and say, hey, what's the image of that subset? And just look at the arrows out of that subset. And then inverse images, we go back the other way. Given a function, f from A to B, so we know A is the domain, B is the codomain, and subsets, we got to play the game with subsets. C is going to be a subset of the domain A, and D is going to be a subset of the codomain B. We define 1. F of C. This we read as F of C. Oops, that's an of. Or we read it the image of C under F. So what is it? It's the set of Y values over in codomain B such that there exists an X in C where f of X hits that Y. F of X equals Y. And so the intuition, folks, behind this, and it is nice to have an intuition. F of C is the set of elements in B that get hit by arrows coming from elements in C. Okay. And we'll, of course, we'll look at examples, but let's go ahead and get the other definition, the inverse image of D. F to the -1 of D. Remember, D is a subset of the codomain. So when we see F to the -1, we're looking backwards. It's the set of X in A such that F of X is in D. In other words, it's the X's in A whose arrows wind up inside D. So the way we read this is the inverse image of D under F. We're looking backwards, like we kind of run backwards along the arrows. And the intuition is nice to have here. F inverse of D is the set of elements in A, the domain, whose arrows terminate or end inside set D somewhere. They hit something in D. Okay? So let's give it a shot, shall we? Let's go back to example 3. And let's play the images and inverse images game. This might be one of the times when PowerPoint might be cool to have. You know, I'm not a PowerPoint person. It's not that I don't know how to make PowerPoint. It's just that I like you to see what's going on. So, and I like you to see how long it takes to actually do stuff. I like to model writing mathematics, doing mathematics. It's like a Zen thing here. All right, so remember H was this set. 1 went to B, 2 mapped to C. Three mapped to E, 4 mapped to E, and 5 mapped to C. So A. Oh, a picture might be good. Get a little wider. Okay, so we're going to find H of C, where let's just start with C is going to be the set containing 1 and 2. So here the function isn't F, it's H. So it's H of C instead of F of C. But according to the definition, it's the Y's over in the codomain. Of course, here the domain is X and the codomain is Y, it doesn't matter. But in the codomain, where there is an X and C that hits the Y. So let's look at, it's like you can just think about 1 and 2, like you can put them together in a little bag. That's a little subset of X called C. And we're just looking for the arrows that come out of this subset that contains 1 and 2. And we're looking to see what gets hit out of that subset. So what is the image of C under H?
Professor, why is A going into C and not B?
Let me see. Did I not, let me check. Did I do something wrong? One go, yeah. Hey, nice job. Extra credit. The reason it's not going where it's supposed to is the old Dr. Good is slipping. She's slipping. Email me for that. Thank you. Let's fix it. Nice. Somebody's actually awake. 1 is supposed to go to B. Ah, nice. That's going to make a difference, isn't it? Very good. Is that right? Did I have it right now?
Yeah.
Yeah, excellent. So what is the image of C? In other words, let's look at the arrows coming out of this subset C. Where do they go? What do they hit? What elements are getting hit? Anybody?
B, C.
5 and 2.
B and C? Did I hear B and C?
I said B, C, E.
B, C, and E.
Yeah.
Okay, that's the range of H. The range of H is B, C, and E, but we're asking for the image of just this subset of X.
That's B and C.
Just B and C, right? See, because 1 maps to B, 2 maps to C, and that's all we're looking at. We're just, we're just looking inside this little red subset and asking, where do the arrows coming out of this little red subset go? And they hit B and C. So since H of 1 is equal to B and H of 2 is equal to little c, H of the subset C is the set containing little b and little c. Everybody with me? All right, so I'm gonna give you a couple more sets C, and you see if you can find H of C for these sets C, okay? What if C is got 3 and 4 in it? And what if C has got 2 and 5 in it? And here's the definition of the image. There, everybody can find those. Since H of 3 is E and H of 4 is E, H of this C, we could call, we could call this C1, C2, and C3 since they are different. Why don't we do that? This will be C1, C2, and then it'll be C3. H of C2 is, I'm just getting the singleton set E for H of the second C2, right? Is that what y'all are getting?
Yes.
Thank you. And finally, what is H of C3? So you can, yeah, it's just little c. You can look at the arrow diagram, but you can also just look and see where 2 mapped to, 2 went to C, right? 5 went to C, so you know that C is the only thing that's getting hit out of this subset of the domain, right? All right, so now shall we play the inverse image game? Let's play the inverse image game. So here's the definition of the inverse image. We're going to look backwards and see what elements hit the elements in D. Okay. So find H inverse of D where, okay, for our first one, let's let D, I'll call it D1, be the set containing A, B, and C. So what we're doing is we're looking backwards to see what hit A or B or C. Here's our, let me fold this out and get it out of your way. Here's our definition. It'll be the elements over in the domain. The domain here is called X, not A, doesn't matter. Such that F of those X land in D. So we're just asking what elements have arrows that land in this subset D1. I'll draw, so we're looking at this subset of the codomain. It's got A, B, and C in it. So we just look at the arrows that landed inside this green subset and find the X elements that shot those arrows into this green subset that contains A, B, and C. So what would that be?
Would it be the elements 1, 2, and 5?
Yeah, 1 maps into D1 because it hits little b. 2 maps into D1 because it hits C. And 5 maps into D1 because it hits C. Right? So H inverse of D is the set containing 1, 2, and 5, since H inverse of A was nothing hit it, but H inverse of B was the element 1, and H inverse of C was both the elements 2 and 5. So 1, 2, and 5 send their arrows in to hit this subset, you know, these elements in this subset. Questions? Should we do another one? Let's do a couple more and just make sure everybody has got it. How about D2? Let's let D2 be the set containing A and D. These are subsets of the codomain Y. So what elements back here in the domain hit A or D? Anybody? Little a or little d? Did anything hit A? Does any arrow hit A? Nope. You know, A does not appear as the second coordinate anywhere, so nothing is hitting A. What about little d? D does not appear as a second coordinate. It does not get hit by an arrow. So guess what? Oh, this is D1. H inverse of D2 is empty because the inverse image of A is empty because nothing hit A, and the inverse image under H of D is also empty. No arrows hit either one of those. So the inverse image of this subset is the empty set. And finally, for D3, wow, I'm going to have to steam that piece of paper or iron it or something to get it flattened out to scan. Let's do one more. D3 is going to be the set containing E. What is the inverse image of D3?
Three and four.
Yeah, because 3 and 4 both map to E. 3 hits E, and so does 4. So the inverse image of just the singleton set E is the set that has 3 and 4 in it. Questions? Okay, so that's it for images and inverse images. That is section 7.1. And now we are ready to start section 7.2. Properties of functions. There are two famous properties of functions that are very important anywhere, really, in higher mathematics. First, we're going to look at the one-to-one property. Here's the definition. A function f from A to B is one-to-one if f of x1 equaling f of x2 implies x1 is equal to x2. So here's the intuition. No y in B is hit by more than one arrow. Or you could say it this way. Each y in B is hit by at most one arrow. Doesn't have to, it could be less than one arrow, but at most one arrow. Or you could think about it this way. Any y in the codomain B appears as the second coordinate of at most one ordered pair in F. Or you could think about it this way. F inverse of y has at most one element. Could have 0, but at most one element from the domain A for all y and B. So each y could be hit at most once. Now here's the definition of onto. I think of onto, you know how the function is heading toward B, it's shooting at B. B is the domain, you know, it's like the target that the arrows are shooting at. May not hit everything in B, but the arrows are shooting toward B. I think of onto is like a wall-to-wall carpet that goes and covers B up all the way, like a wall-to-wall carpet. A function f from A to B is onto if for all y in B, there exists some x in A. So for all there exists, Tarski comes back to haunt us. So for each y in B, there is some x in A such that f of x equals y. All right, so what's the intuition here? Every y in B gets hit by at least one arrow. Or you could think of it as every y in B appears as the second coordinate of at least one ordered pair in F. Maybe more, but at least one. Or kind of the cleanest way to think about it is that the range of F, the set of points, you know, that get hit by F, is the entire codomain. Everything gets hit by an arrow. That's what onto means. Oh, I guess I should have put onto here. Sorry, I didn't skip a line there. All right, let's look at an example. I'm going to start a new page. We're going to let A be the set containing 1, 2, 3, 4, and 5 again. Why not? And B be the set containing S, T, W, Y, and Z again. Why not? F is going to be this function from A to B. 1 maps to S, 2 maps to T, 3 maps to W, 4 maps to Y, and 5 maps to Z. Okay? So, you know, F is going from A to B. Is this function 1-to-1? Okay, so we'll just slide this up. A, is F 1-to-1? So listen, the 1-to-1 property is kind of like a fidelity clause. It says that if you look at the elements in the codomain B, each one of those elements Y cannot have more than one partner from A. At most, one arrow can hit any given B, Y in codomain B. That's what it means. So let's draw an arrow diagram. This can actually really help us. That way we can see what's going on. 1, 2, 3, 4, 5. S, T, W, Y, Z. F is going this way. This is A. This is B, and 1 maps to S, 2 maps to T, 3 maps to W, 4 maps to Y, 5 maps to Z. This is kind of like the simplest first example. Is F 1-to-1? What do you think? Is each Y and B hit by at most 1 arrow? Or does any Y and B appear as the second coordinate of an ordered pair at most once? What do you think?
Yes.
Yes, of course. Yes. And another way to think about it is the inverse image of each element in B has at most 1 domain element. So at most 1 domain element hits any given codomain element. What about onto? Is F onto? Let's look at the intuition behind onto. Here's our onto property. Every Y and B gets hit by at least 1 arrow, or every Y appears as the second coordinate of at least 1 ordered pair. Or another way to think about it is the set of all the elements in the codomain that actually get hit, that's the range, is the whole codomain. Everything gets hit. So is it onto?
Yes.
Of course it is, yes. Every element in B gets hit by an arrow. Okay, so one more time. For 1-to-1, each element in the codomain gets hit by at most 1 arrow. Nothing's getting hit by 2 arrows. Like over here, this function was not 1-to-1 because 2 different elements hit C, right? 2 arrows are hitting C, so it's not 1-to-1. That would be enough right there. It's also not onto because nothing hit A. So this function H is not onto Y because it missed A. No arrow, it also missed D, but it's enough that it missed A. Okay. So let's look at another example. A and B as in example 5. Okay, same A and B, but here G is going to be a different function, and G is going to be this function where 1 maps to S, 2 maps to S, 3 maps to W, 4 maps to Y, and 5 maps to Z. Okay, so, is G 1-to-1? Is G 1-to-1? 1-to-1. Here's the intuition behind 1-to-1. No Y is hit by more than 1 arrow. Or no Y appears as the second coordinate of more than 1 ordered pair. Each Y, any Y appears as the second coordinate of at most 1 ordered pair. So is this a 1-to-1 function? And here's the definition of 1-to-1. Yeah, it's not. Why not?
Because S is the second coordinate in 2 of them.
Yeah, it's second coordinate in more than 1 ordered pair. And in fact, if we want to actually use the definition of 1-to-1, G does not satisfy that definition because it's an if-then definition. And so put a G here instead of an F. If G of x1 equals G of x2, then x1 has to equal x2, all right? G doesn't satisfy that. G satisfies the negation where G of x1 is equal to G of x2 and x1 is not equal to x2 for x1 equals 1 and x2 equals 2, right? So let's just write it like this. Say G of 1 is equal to S and G of 2 is equal to S, but 1 is not equal to 2. So we have G of x1 is equal to G of x2, and x1 is actually not equal to x2. So the negation holds. So, the one-to-one negation is actually what's going on for G. We're getting the P, the hypothesis that the function sends x1 and x2 to the same place. Their images are equal, and those elements were not equal back in the domain. Good. Let's take a look at the other question, of course, that we have to ask. Is G onto? What do you think? We're looking at G. This is our G. Here's our definition of onto.
I said no.
Okay, I didn't hear you.
I said no
Yes,
because
good.
P is an element of B, which is not hit in G.
That's right. Yeah, we actually do need to see B here. T is an element of B, but it is not the second coordinate. It's never hit. Notice T is an element of B, but T does not appear as the second coordinate in any ordered pair in G. So you don't actually need to see a picture in order to interpret this. You can do it just by looking at the ordered pairs. So here's something to notice. Look what happened with this example 5. It was 1-to-1 and onto. And A and B are finite sets of the same size. They each had 5 elements. Now, this F was 1-to-1. Each element in the codomain only got hit by 1 arrow. At most 1 arrow. But each actually did get hit by at least 1 arrow as well. So here's an interesting thing to notice. If A and B are finite sets having the same size, same number of elements, right? Then, in fact, if F is 1-to-1, oh, I better tell you F is going from A to B, my bad. If F, a function from A to B, is 1-to-1, then F must also be onto. Think about it in the context of this picture. If each of these elements has at most 1 arrow, then every one of them has to have at least 1 arrow because it's the same number of elements back here shooting arrows as there are elements to hit. The converse is true. If F from A to B is onto, then F must also be 1-to-1. Okay. If it's onto, it's got to be 1-to-1. Look, if everything is getting hit, in other words, if it's onto, if everything gets hit, then there'd be no way that two different elements in the domain could hit the same element, because there aren't enough elements over here. There's the same number of elements in the domain as the codomain. If everything in the codomain gets hit, then each one of these must go onto a separate element in order to be able to hit all of them, because there's the same number of elements here and here. Does that make sense? And think about it. These are both if-then statements. This is an original if-then statement. This is its converse. We know the contrapositions of these are also true, right? So if F isn't onto, it can't be 1-to-1. If F isn't 1-to-1, then it can't be onto. So it's a real if and only if. In other words, if A and B have the same size, they're finite elements, a finite number of elements, F is 1-to-1 if and only if F is onto. That's the only way that can happen if A and B have the same number of elements. That's whenever the size of A equals the size of B for finite sets A and B. It's kind of fun just to think about it. Now, what if A and B have different sizes? Let's look at an example where A and B have different sizes. That might illuminate some of this for you. Here's an example. Let's let A be the set containing 1, 2, 3, 4, 5, and 6. Aha, finally something a little different. And let's let set B be the set containing S, T, W, Y, Z. Is it possible to construct a function f from A to B that is both 1-to-1 and onto? So, I mean, you can draw a little picture, right? Try to kind of get your head around what we're looking at. Draw an arrow diagram. And we're trying to build an F from A to B that is both 1-to-1 and onto. Is that possible?
Yes.
Okay. Explain to me how we can build an onto function. That would hit everything, right? Onto is like covering it up with a wall-to-wall carpet, right? Do we have enough elements to hit everything in B?
Yes.
We do have enough elements to build an onto function. But could we build a 1-to-1 function where each element in B gets hit by at most one arrow?
Yes,
Oh, really? How many elements are in B?
5,
How many elements are in A?
6.
By definition of a function, every single element of A has to map somewhere. We cannot leave any of these out. Each element of the domain has to have an arrow coming out of it, exactly one arrow. Do we have enough elements over in B that we can spread those arrows out and never have two arrows hitting the same element in B?
No.
We don't have enough elements in B because B is smaller. See what's going on, Hans?
Yeah, I get it now. I misunderstood.
But that's okay. I mean, that's why we're thinking about it. So the answer is no. While we can, no, let me just say we can. We can build an onto function. We can construct an onto function f from A to B because there are enough elements in A to have enough arrows to hit every element in B. But we cannot, no, we can construct an onto function, but we cannot build a one-to-one function. From A to B. Because the size of A is bigger than the size of B, which means at least two elements of A have to hit the same element in B. Must map to. That's the actual mathematical phrase, map to. In other words, hit the same element in B. Everybody making sense out of this? Now I'm going to give you one to do later now. Example 8. Same A, same B. Can we construct a function H from B to A? So the domain is going to be B, the codomain is going to be A, using the same A, same sets, A and B from example 7. So that H is one-to-one and onto. So you can think about it and enjoy that process. I want to point you to new good stuff. Let me share my screen with you and bring up a blackboard. Bring up our Blackboard site. Oh, it's gonna make me log in. Give me a sec. Let me log in because this you're gonna wanna see, folks. You're gonna wanna see these goodies, these goodies. Holy cow. All right, here we go. Got a chat. Don't forget to record. Oh, that was you guys on. Yeah, that's awesome. Let's share the screen. I'll go to the student preview. Okay. Check this out. This is in my way. Okay, I'll move it. Remember the good stuff folder? It's been a long time. Chapter 7 review materials because I care. Oh ho! This is from a prior test from several years ago. Review on functions. Not very clear, but this is going to be a nice review sheet for you. Okay. And then the solutions. Complete solutions. Okay. I'll be doing the same thing for chapter 8. Because time's a ticking. And I know that it's very difficult to absorb this much material this quickly. Okay? You're welcome. Oh, the other thing that's happening is it's not happened yet, but let me just show you. Here's my YouTube channel. There's a new playlist in town. Math to, and it's open. It's not even, you don't even have to have you know, it's public. Math 263 lectures. Welcome to our lecture about binary relations. Okay, we don't need to hear me anymore with my big mouth open. Oh my God, let me close my mouth. Finally, she closes her, oh God, she never closes her mouth. But anyway, this is the first of several lectures that I'm recording about chapter 8. So that Tuesday, when we get together, you're going to be able to just talk about chapter 8 with me. We'll have more of a discussion and a workshop, okay, than a lecture. Okay. Did I stop sharing? Did I show you the playlist? Or was I not sharing? Oh, good Lord. I say good Lord. Not firing on, so I'm tired. Okay, so it's a new playlist. If you go to playlists, it's 263 lectures to accompany, right? And it's public, and there's one video in there right now. And it's about section 8.1, part 1. I'll record part 2 tonight, and section 8.2 and section 8.3 I'll record tomorrow. I'll post the notes somewhere in Blackboard, and I'll send an announcement to let you know where these are. That's why I set my screen up, you know, and like I said, the notes will be posted. This is chapter 8 stuff. Okay, I can stop sharing now. All right, good. Okay, so that way you can look at stuff ahead of time. Let's think about infinite functions now. We've been looking at a bunch of finite examples, folks, and that's not actually, you know, what you always see. You don't always just see finite examples. Here's one, just Just to look again at one that you know, f goes from the reals to the reals, and it's defined by f of x equals x squared. Again, we looked at this at the beginning of class, but it is an example of an infinite function. If there are an infinite number of ordered pairs in this function, we couldn't possibly list them all, but we do have this rule that tells us f is the set of ordered pairs of the form x squared, where x comes from the reals. We could also say x squared is in the reals, but that would be redundant. We know that x squared is real if x is real, right? And it looks like this. And, you know, you can ask yourself questions about this. You know, A, is F onto? Now we're told that the domain is the reals and the codomain is the reals. We're told that. So is this function onto? All right, so in other words, does every element in the reals appear as the second coordinate of some ordered pair in this function? Does every element in the reals get hit by an arrow? I mean, you know, it'd be hard to draw an arrow diagram for this. But one way to think about it is we're trying to hit the y-axis. This is the codomain axis. Whereas the horizontal is the domain axis. And it's also a copy of the reals. Do we hit everything in the codomain? Does every real number appear as a second coordinate?
Yes.
Okay, let me
Oh,
ask
never
you.
mind. Never mind.
Never mind. Like, look at -1. Does -1 appear as the second coordinate in any ordered pair in F? Can x squared ever equal -1 for a real x? You see, notice how the graph, see the y coordinates are associated here. Like if you go across here for this particular x right here. So here's an x value. You go up to the graph and then you go across, and that's the f of x value, you know, this height right here. The height is the y value. So we can hit this one, you know, with this x here, you know, we can hit this y value, we can hit this y value here by finding, you know, that x value. And we can even hit 0 with x equals 0, right? But can we hit -1? Does this graph, does this curve have ever achieved the value -1? Nope. So no, because no negative real number appears as a second coordinate of any ordered pair. In F. Because x squared is never, you know, because x squared is always greater than or equal to 0. That's why the graph is above or at the x-axis. X squared is always greater than or equal to 0. So all the y values are up here above or on the x-axis. There are no, the curve isn't ever going to dip below because there are no x's whose y values are down below. See what I mean? All the y values are at or above y, the y equals 0 value, right? Because the second coordinate is never gonna be negative. That's why this curve doesn't, go down, because that's not what this curve does. This curve stays above or at the x-axis for all x values. Is f 1 to 1? Oh, that's part B. Is f 1 to 1? Let's just look at, if f of x1 equals f of x2, then x1 has to equal x2. That's the definition of 1 to 1. Right? That if x1 and x2 actually hit the same, have the same second coordinate, then that means the x1 and x2 are actually the same number. Is this a 1-to-1 function? Did you ever hear of the vertical line test for functions where you just move a vertical line across the plane and just make sure that the vertical line never touches the graph in more than one point? And that's a test for a function, the vertical line test for a function. Well, you know what? The test for one is a horizontal line test. You move a horizontal line through the plane and you check that the horizontal line never touches the graph in more than one point at a time. But look what happens. Look what happens. Like here, this horizontal line. It's the same y value. See, the y value is right there. That height is the y value. But there's an x over here, x1, that achieves the same height or y value as the x over here that's the same distance from the origin, but on the other side, x2. Yeah. F of x1 is this height, is this y value, but so is f of x2. It's the same value, but x1 and x2 are not equal. They're on different sides of the y-axis. See what I mean? So the answer, is it 1-to-1? No. Think about this. Let x1 equal -2 and x2 equal +2, right? F of x1 is f of -2. That's -2 squared. That's 4. But f of x2 is f of 2, but that's 2 squared, because that's what this function does. It squares whatever you drop in there. And that's also 4. But -2 is not equal to 2. So we have, f of x1 equals f of x2. But we also have that x1 is not the same as x2. So you've got two different arrows hitting 4. One shooting from -2, it hits 4. But you also have an arrow shooting out of domain element 2, it hits 4. But -2 and 2 aren't the same elements. So you've got two arrows hitting 4. It's not 1-to-1. Does that make sense? I need a nod. I need something, folks. Anybody, anywhere,
That makes sense.
Does it make sense? Okay. So, I mean, there are lots of infinite functions that you can look at and ask the question, is it 1-to-1? I'll give you a classic example of an infinite function that is always onto and 1-to-1 if the codomain and the domain are both the reals. Here's a classic example of an infinite function that is 1-to-1 and onto. And that is the linear function. So f from the reals to the reals defined by, this might bring back old memories, f of x equals mx plus b, where m and b are just real numbers. Remember, m is the slope of the line. And B is the y-intercept of the line. Remember all that? And if we graph a straight line with slope M and y-intercept B, I'll just draw one that's got a positive slope, okay? I mean, if it has a positive slope, you know, the line rises up. If the line has a negative slope, it, you know, it falls down as you read left to right. But here is, you know, here's B, the y-intercept. You know, that's the y value. Okay, we didn't go left or right at all. There, it's 0, comma B, really, technically, but we just say B because everybody knows that if you're on the y-axis, then the x value is 0, right? The x value is how much you go left or right. If you're sitting on the y-axis, you didn't go left or right at all, so the x is 0. You didn't move away from the origin. But then the B is the height, and you know, it could be down here, but I'm just drawing this line, y equals mx plus b for a B that's positive and a slope M. Slope is the rise over the run. Remember the rise over the run. If you take any 2 points on the line and you look at this height right here, you know, that's the rise. And then you look at this width, you know, that you traveled here. This is called the run. And M is equal to the rise over the run. Remember all that good stuff? Anyway, this is a one-to-one and onto function. Every single y value will eventually have, you know, no matter how far up you go or down you go, if you pick a y value, then you can find the corresponding x that achieves that y value. No matter how far down you go, this line will keep going down forever. So even if your y is way down here, this line eventually you'll find an x way out that way that would hit a really low y. Same way with up here. Any y up here, you know, if you go far up enough of the line, you can hit any y no matter how high it is. This is definitely on to. It's on to. If y is in the reals, then we can find x in the reals that makes y equal mx plus b true. You know, how? Just solve for x in this equation, right? Solve for x. X will be y minus b over m. M's not 0, okay? If m is 0, it's a horizontal line, okay? We're not talking about those. Because a horizontal line is not onto. A horizontal line would only hit one y value. It's very, very not one-to-one. But if m is not 0, there's some slope, okay? And you'll hit every single y value. And no x hits more than one, no y is hit by more than one x. So it's also one-to-one. And it's kind of easy to prove that a straight line is one-to-one because remember, we have the definition. If f of x1 equals f of x2, then x1 has to equal x2. And that's super easy to prove if your equation of your line is that f of x equals mx plus b, right? So the proof that it's one-to-one is just assume the hypothesis and we can prove the conclusion. All right, so proof, assume x1 and x2 are elements of the reals, they're domain elements. Also, this is supposed to be an also, assume f of x1 equals f of x2. What do we wish to show? We wish to show x1 is equal to x2. It's going to be super easy because this is a linear equation. Okay, that's our equation right there. So set f of x1 equal to f of x2. So f of x1 is literally equal to mx1 plus b. We're going to set that equal to mx2 plus b, which is f of x2. So we set these two equal to each other. We're just looking in here, okay? We're just looking at this part. And then what do? Subtract b from both sides, right? Then you get m x1 equals m x2. And what do? M is not 0, folks. We can divide both sides by m, and x1 equals x2. Ta-da. It's real easy to prove that a linear function is one-to-one. This is classic stuff. All right. Now, this all worked out beautifully because we picked a linear function that maps from the reals to the reals. But we can make this more interesting by changing the domain. I still want an infinite function. I still want an infinite domain. But I'm going to use a different domain. I'm going to use Z. Same idea. I'm going to even make it a little easier. I'm going to make it harder in one sense, but easier in the other sense. I'm going to use actual numbers. We're going to let G go from Z to the reals. So I could do the reals, but I'm going to go say Z to Z. Okay, it's still infinite. Z to Z be defined by this. G of X is going to equal 2x plus 3. And in fact, to be really nice, let me change x to n to emphasize this is an integer. G of n is equal to 2n plus 3. Definitely a linear situation. A, is G 1-to-1? Let's just do that first because it's just like the proof that we just did. This proof, that F was 1-to-1, it works for this G as well. Super easy. Yes. Assume G of x1 equals G of x2. We wish to show x1 equals x2. It's the same argument, okay? You can finish it, okay? You finish. It's this exact same algebra we just did. But hey, now, what about this question? Is G onto? See, that's what's going to happen. That's going to be different. You see, again, this F, this line is onto. No matter which Y you pick, no matter how high up it was, if you pick a Y way up here, you could find an X way out here that would hit that Y, okay? Not so here. Not at all. Let's just take a look. Let's look at the images of some sample values for n, okay? All right, well, so what about if n is 1, okay? That's an integer. What is G of 1? Here's our equation for G, right here. What's G of 1, everybody? Quickly. What is G of 1? It's 5. It's 2 times 1 plus 3, which is 5. Okay, great. Now let's check n equals 2. Remember, there's space between these numbers, all right? These are integers. They're discrete. There's room between them. What about when n is 2? What is G of 2, everybody? Anybody?
8.
Is it my speakers that are failing?
Is it 7?
It is 7. Thank you, Chloe. 2 times 2 plus 3 is 7 in my book. Thank you. Maybe my speakers were turned down too low because I've been screwing with my speakers. Okay, G of 3.
Nine?
Yeah. What's going on? Let's look at g of negative, no, let's look at g of 0. And then let's look at g of negative 1. What's going on? What is g of 0?
3.
It is. G of 0 is 3. What's g of negative 1, folks?
1.
It is. Thank you. What does it look like the range is? What's getting hit by this function? What does it look like it's getting hit?
The odd numbers.
Yeah, it looks like we're hitting the odds, and we are. We're hitting all the odds, but we're not hitting any of the evens. And we know z has both evens and odds. We're not going to be able to hit any of the evens. This function's not onto. Never hits any evens. The range of g is going to be 2z plus 1. G never maps to any even number. Hey, if you draw the graph, it's kind of cool looking. This is skewed a little bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Skewed a little bit, but 1, 2, 3, no, negative 1, negative 2. In other words, my x-axis and my y-axis aren't exactly drawn on the same scale, but I should have my positive x-axis and my negative x-axis at least being drawn on the same scale. Could at least do that. That's more like it. Okay, so g of 1 is 5. So when x is 1, when n is 1, the y value is 5. When n is 2, the y value is 7. When n is 3, the y value is 9. I mean, it's supposed to be straight-ish, right? The line is, but it's got holes. There's gaps. When, we're at 3, it's 0. Negative 1 is at 1. See what I mean? There's a bunch of gaps. And none of these even numbers ever get hit. They're in between the gaps. There's no x that hits, 4 or 2 or 0 for that matter. So how do we prove, prove G is not onto? All right, so to prove it's not onto, let's just review the definition of onto. For all y in B, there exists an x in A such that f of x equals y. And this is for f mapping from A to B. That means for each y in the codomain, there is some x in the domain that hits it. So that the image of x is y. So the negation of that definition is there exists some y in B such that for every x in A, f of x is not y. In other words, there's some y over here in B such that for every single x won't hit that y. In other words, that y gets missed. So, for our proof, G is not onto, consider, your favorite even number. Somebody give me an even number. Oh,
2.
2, yeah. I meant to call it y. It's the y. It's a range value. Consider y equals 2, right? We're going to prove that no integer hits 2. If f of x was equal to 2, then f of n, my bad. If f of n was equal to 2, then 2n plus 3, that, that's f of n. Remember, f of n is 2n plus 3. Oh, g, my bad. Jeez. G. Good Lord. G of n equals 2 means 2n plus 3 equals 2, right? But what does that mean? Solve for n. What would n have to be? N would have to be -1/2, wouldn't it? Take the 3 over, divide both sides by 2. But -1/2 is not an element of Z, the domain of G. So the number that we need to hit the codomain value 2 doesn't exist in our domain. So I just wanted to show you, kind of a cool example like that. Where, well, what makes it interesting? The continuous version of this graph, if you put a 2x plus 3 here, instead of 2n plus 3, 2x plus 3, it would be on 2 and 1-to-1. 1-to-oneness doesn't fail. I mean, just because we erased a bunch of the line, the 1-to-oneness doesn't go away. That still holds, but the onto-ness gets blown out of the water. I think that's interesting. Same equation, different domain and codomain, different properties. All right. That's all I'm going to say about this section 7.2, and you're going to get in there and you're going to actually do some reading and look at some examples that Ep gave and work on that review sheet. And we're going to move on. We still have good time. We're making good time. We're doing good. We're doing well. And I want to talk to you about function composition, because this is something that students tend to not understand. And I think it's important. So how do we compose functions? You might remember this from high school. You might not. So I'm going to think of functions as machines, little machines, okay? So I'm just going to draw a picture. If I have a function f, it's like I'm going to think of it as a little monkey grinder, okay? And this is the little handle. Makes that song too, okay? And what happens, what does it do? Okay, we drop in an x from the domain. Right? We drop a little x from the domain of the function f, and then it grinds on x, and out comes y, which is f of x in the codomain. Okay? That's the way I like to think of a function. Why do I like to think of a function that way? Because composition then becomes a little easier to understand. Composing two functions. So we're going to suppose f is a function from a to b. Remember, when I use this notation, I mean it is a function. And g is a function that maps out of b and into c. And our definition then is, oh, this is the definition. Started there. We have to have that information to make this make sense. Then the composition of G by way of F, denoted by G open hole F, is a function from A to C defined as follows. For all X in A. F happens first, folks. It's G by way of F, also called G of F. For every X in the domain of F, okay, in A, G of F of X is defined to be, this is actually how it's defined, to be G of F of X. Okay, now, students see this notation and they go, what? Let me draw a picture. All right, so F acts first. It's G by way of F, G of F. And even though we read left to right, F happens first. G of F. So look, here's F. Again, a little monkey grinder. We are going to drop in an X from the domain of F. So it's coming out of A, drops, an element from A. Out comes F of X. Now that's in B because the domain is A, but the codomain of F is B. So in goes an X, F grinds on it, out drops F of X. Guess what happens then? F of X gets dropped into G. It's a different function maybe. G grind, and look, why can we do that? Because the domain of G is B and F of X lives in B, so it can drop into G, and then G grinds on F of X, and out comes G of F of X. That is defined to be G of F of X. Okay, so I like to think about it this way, because then it makes sense. And where does G of F of X live? It's in C, because that's what G does. It sends elements from B into C. If we want to draw a picture, it's going to be nice, and we'll do that for an example here. All right, so we're going to let A be the set containing 1, 2, 3, and 4. B be the set containing X, Y, W, Z. And C be the set containing A, B, and C. Okay? And we're going to define F from A to B and G from B to C, where F is this set of ordered pairs. 1 is going to map to X. 2, remember F goes from A to B, so elements of A map to B. 2 is going to go to Y. 3 is going to go to W. And 4 is going to go to W. G maps from B to C. G is going to send X to A. It's going to send Y to B. And it's going to send W to B. And it's going to send Z to C. Okay, so every element of the domain B gets mapped to exactly one image in C. So these are functions. A, find G of F. What is its domain? What is its codomain? All right, so we want to make sure we understand here that. Here's our little picture over here. All right, so Hey, I'm gonna draw it this way though. Here's A. F acts first. Here are the elements of A. 1, 2, 3, 4. Here's B. B's got X. I've got to try to stay out of my own way. Y, W, I'm putting the letters right above the points. Z, because I don't want them to be in the way of the arrows. So F, I'm going to do in green. F is going to map from A to B. G is going to pick up and map from B into C. I'll do it with red, okay? And the codomain of G just has 3 elements. It's set C. It's just got A, B, and C in it. Okay. All right, so we can draw the arrow diagram first. So 1 maps to X. So 1 is going to map to X. We'll do F first. 2 maps to Y. 3 maps to W. And 4 maps to W. Okay, great. Now, G sends X to A. So X is going to map to A. Y is going to map to B. W also maps to B. And Z goes to C. Okay, so the composition from A to C is G of F, not F of G, G of F. This is G of F from A to C. Okay, now let's find G of F. But first of all, what's the domain of G of F? G of F starts in A, ends up in C. So G of F maps from A to C. A is its domain. C is its codomain. B is just like a layover. Does that make sense? You with me? Osmond, does it make sense? Lisa?
Yeah.
Everybody good? You still with me? Good. Here we go. So we're gonna find G of F. All right, so there are a couple ways to do it. G of F of 1. All right, we can do it this way. Let's just think about it using the arrow diagram. 1 under F goes to X, right? And then G picks up and sends X to A. So that's one way to think about it. You know, using the arrow diagram, just chase the arrows through. 1 goes to X, goes to A. So in fact, G of F of 1 is equal to A, okay? But you can also think about it this way. G of F of 1 is, by definition, G of F of 1. That's actually how this, function is defined. But what's F of 1? Well, F of 1 is X, so it's G of X. And what is G of X? Oh, X goes to A. It's A. See what I mean? So you can do it either chasing arrows through the diagram, or you could do it algebra. So pictures versus algebra. Take your pick, whatever your pleasure is. Let's do G of F of 2. So 2 maps to Y using the picture under F. And then G sends Y to B. So G of F of 2 is B. But if we want to do, the algebra, it's G of F of 2, but that is G of F of 2 but f of 2 is y, so we're looking at g of, well, f of 2 is y, so g of y, and g of y is b. So you can get it the same way. Same thing, different way. All right, so we'll do the last two. So g of f of 3. Okay, so 3 goes to w, and then w goes to b. Four goes to w, and w goes to b. Right. So the ordered pairs, you know, is 1a. 2 goes to b. Here, g of f of 3 turned out to be b, so 3 goes to b. G of f of 4 turns out to be b, so 4 goes to b. So, I mean, that's the answer, of course, then is g of f is equal to the set of ordered pairs. 1 goes to a, 2 goes to b, 3 goes to b, 4 goes to b. Okay? And you can fill in this algebra here. You know, you do the alternate. You finish. All right. Finally, just a little food for thought. What time is class over? 8:45 or 8:50?
8:45.
That's 8:50. All right. See you later. Find. Haha, you get to play the image game and the inverse image game. G of f of d, where d is the set containing 4 and 5. And then you can find g of f inverse of e, where e is the subset of the codomain that just contains that element C. Now, we don't have time to do another one, but I'm going to include this page of notes with another example of function composition, okay? Just so you can see another one, all right? Now, there is one more thing. We have 5 minutes. We're going to talk about it. F inverse. The inverse image of F. Might be a function, might not. Here's the definition. It's real easy. Given a function f that maps from A to B, we define the inverse image of f. It's not necessarily a function, denoted by f to the minus 1 as follows. F to the minus 1 is the set of ordered pairs B comma A, where A comma B was in F. In other words, you just take the coordinates and you switch them. That's the inverse image of F. And here's an example. This is actually going to be example 14 because example 13 is the one that I'm just going to insert in the notes for you to read later. And that is that F from A to B, where A is going to have little a, little b, little c, little d in it, and B is going to have little x, little y, little z, and little w in it. And F is the set of ordered pairs A maps to x, B maps to y, C maps to y, and D maps to w. Find F inverse. It's super easy. All you do is you just look at the ordered pairs in F and switch the coordinates XA, YB, YC, WD. It's that simple. If you wanted to draw the arrow diagram for F inverse, you could just make the arrows go the other way, or you could even switch A and B around. But this is the thing. The real interesting question is F to the minus 1 a function? Is this inverse image actually a function? Well, notice F inverse in example 14 is not a function from B to A. Why not? Well, look. Y has two images. Y map is going to B, but Y is also going to C. So it fails the uniqueness part of the definition of function. It also fails the existence part because B has Z in it, right? And Z didn't go anywhere. Z is not the first coordinate of any ordered pair. So it's not a function. So the real question is, why not? It's because F is not both 1-to-1 and onto. In order for the inverse image to be a function, F has to be both 1-to-1 and onto. So when is F inverse from B to A a function? If F from A to B is 1-to-1 and onto, then F inverse from B to A is a function. And I'm going to just show you a little picture I've already drawn to explain why that is. I want to show you what goes bad. If F isn't 1-to-1, what goes bad? If F isn't onto, what goes bad when we look at the inverse? All right, so I've got a quickie pick. Here's a function. It's not 1-to-1, is it? A1 and A2 both map to B. Two different arrows hit B. It's not 1-to-1, right? So when you build the inverse function, B has to go back to A1, but it also has to go back to A2. So B pairs up with two different second coordinates, and that makes the uniqueness property, property 2 of a function, fail. All right, what about if F isn't onto? See, look at this B. It didn't get hit by an arrow. Let's think about F inverse. This F, is not onto. It didn't hit everything. It didn't hit this B. Well, think about what F inverse would look like. there would not be an ordered pair with B as the first coordinate because nothing paired up with B to begin with. There was no B as a second coordinate in F. So B won't be a first coordinate going back the other way. And so property one will fail. The existence of an image for B going back the other way will fail. That's why F has to be both one-to-one and onto for the inverse image to actually be a functional inverse. And that is chapter 7. And I am beat, but I'm glad you're still with me. Thank you for playing. That light is great. Turn this light off, it's too bright. I just needed it for notes. So any questions? I'm trying to, there. That's much better. Any questions? Any answers? I could use some answers about right now. No? All right, listen, thanks for playing. Thanks for staying. Bravo to those of you who are brave enough to stay and play. I'll get these notes posted here in a little while. You got plenty to work on, right? You've got the review sheet for functions. You've got WebAssign is up for 7.1 to 7.3. You got that to work on. I may not do a special homework. I might just say work on the review sheet. What would you say about that? Does anybody have any feelings about that?
No, that's fine.
You'd be okay with that?
Yeah. So you said that the web assignment is up for
7.1 to 7.3. Is it not up?
I just see 5.2 and 5.3. That's it.
Oh, well, I'll do it right now. I'll do it right now. I'll get 5.6 scheduled and 7.1 and 7.3. They're already created. I guess I just need to post them. Thank you so much for telling me that, Lisa. I appreciate that. Help keep me on task here. I am working hard to keep everything done right now. And I know you understand that better than most. I do. Anybody else? Comments, questions? I'll get your tests graded ASAP.
Are you also going to grade the last special homework and the last quiz as well, or?
The last quiz has been graded. That was emailed to you. The last special homework was emailed to you before the test. Oh, you mean on
always check the-
induction? Induction. Yes. Oh, absolutely. The quiz was graded. The take-home quiz?
Yeah, so I know that you emailed the answers to them.
No, that quiz is graded. Did I not post the grades
No, I don't have any grades for the special
for
homework
quiz
A or
2?
quiz.
Yeah, me neither.
There's no
Yes.
grade.
All right, thanks for the reminder. I'll get those up. But the quiz was before the test, right?
Yes.
Yeah.
Yeah.
You
People, I have really done, I screwed up. I'm putting it on camera. It's on the record. I screwed up. That was supposed to be graded before I know how it happened and I'm very sorry. I really am doing the best that I can.
Well, it's
It's
okay. I
alright.
mean, you sent the answers to it out,
Yeah.
so
Yeah.
And I've had copious office hours if you had any questions. No, that was supposed to be great. I thought I had done it. I had graded it for the other class and I thought I had done, I'm so sorry.
It's okay.
I really am doing the best that I can. But
It's all
definitely
right. Yeah.
the induction gets graded and your tests get graded. It's actually more important for you to get your feedback on induction, right? I know you want your test grade too. But you got to get your feedback on induction before this test on Thursday. I will get it done. I will. Sorry about the quiz. That was a boo-boo. Hey, so, hey, if that's the one's really serious screw up, if that's the worst, that I do with this workload that I'm enjoying so much, and I am enjoying it, but I can live with it. I get an A- instead of an A. Sorry, Lisa. Thanks for letting me know. I am really sorry. Okay. All right.
Professor,
Yeah.
you didn't grade my special homework number 8,
Who is talking?
Osman.
If it was uploaded, I did. Let me double check now and take a look, okay?
I don't see my grade for 8 either.
Me too, Professor.
Same here.
You're welcome. What do you mean? What? How did that not happen? Is homework 8 on 5-2?
Uh,
No, that was before the test as well. That was 5-1, right? Well, let me look at it. Let me look at this. Oh, for God's sake. Lord. help me. Oh, what? I didn't grade that?
yeah, I think this is the one I talked to you about and checked with you about, I think, maybe.
And I didn't realize I had it. Well, last week was a week of weeks. That's all I can say.
Mm-hmm.
I'm glad the semester's almost over. I'll be sure. You know what? You know what I might do? Because at this point, you're not being tested on that. Would anybody object if I just gave everybody 100 to make it up to you? You're not going to be tested on this at this point. Would it make it up to people if I just gave you 100 on the quiz and 100 on the homework?
Yes.
Sure.
Would that make it
Yeah.
up to you? Okay,
Yes.
all right, I'm gonna do that, and I'm so sorry. I'm not gonna say it never happens, because it just did. It's the first time that's ever happened in all my years of teaching. I'm not even kidding.
Well, you've got a lot going on.
We all have a lot going on. That's, it is true that I probably, I couldn't have done it even if I had planned to do it, because I have been just slammed. Okay.
Yeah.
But you know what? 100, I think, kind of takes the sting out. And I did send the solutions. You know what? Maybe that's why some part of me let that kind of slide to the back, because I knew I'd sent the solutions and I was planning to grade it, but I wanted you to see the solutions, right? And so some part of me relaxed, and I just didn't realize that I was relaxing too much. Believe me, I wasn't relaxing. I know you understand, Lisa. I know you get it. I know you do. All right. 100s on those. I'll send the announcement right away. I'm so glad you said something, because I really, truly did not even realize I had not done that. But I will grade the induction homework first thing. And I'm also trying to create these videos. So it's going to be a busy weekend.
Mm.
So, but bravo. I'm going to stop recording now. Thank y'all.